Hello dear students. So today we are going to see the chapter operational amplifier and the topic that is a virtual ground concept and the concept of non-inverting amplifier. So dear students, we already have had an introduction of the operational amplifier in which we saw the characteristics, ideal characteristics of an operational amplifier, in which we saw that is open loop gain, that is AV, that is VO upon V in, that is infinite. Second important thing which we saw, that is input impedance of an ideal amplifier, operational amplifier, is infinite. Output impedance of an ideal operational amplifier is 0. Infinite bandwidth, common mode rejection ratio, CMRR, is infinite. Slew rate is infinite. Input current, that is IN, that is between two input terminals, that is 0. And output voltage, common mode, that is 0. So these are the characteristics of an ideal operational amplifier. But whenever we use the operational amplifier practically, there it is some variation in these characteristics. And remember that in case of practical operational amplifier, see, open loop voltage gain, actually it is not, AV is not infinite, but it is very very high, and it is several thousands ohm, that is open loop voltage gain. Then here input impedance is greater than 1 mega ohm. So remember that input impedance is 1 mega ohm, that is a very high resistance there. Even it can be increased by proper arrangements. So output impedance, it is typically few hundred ohms, that means very small, but it is not 0. So practically bandwidth of the this practical operational amplifier, practical bandwidth in open loop configuration is very small. So by application of negative feedback, this bandwidth can be increased to a desired value for which we are using operational amplifier. Then input offset voltage, practically it should be 0 in ideal, but we get few millivolts as a input offset voltage in practical operational amplifier. And input bias current is present, that is nearly equal to 10 raised to minus 6 ampere to 10 raised to minus 14, that means it is in the microampere range. So the small amount of current is flowing in practical amplifier. So now these are what the specification or characteristics of that practical amplifier. Now let us consider what exactly is the operational amplifier and what are its block. That is a block diagram of operational amplifier. So first stage is input stage. See, we already saw that in case of operational amplifier there are two inputs, that is inverting and non-inverting, and there it is an output, that is VO. So here at the input end we say the V in, but V in is difference of V1 and V2. So here first function of input stage is, see here it is, it consists of dual input, that means V1 and V2, and balanced output. So by taking the inputs inverting and non-inverting, it gives some output, balanced output differential amplifier is there, which gives the difference of both input voltages at the output. It amplifies the difference between two input signal, and it provides high differential gain. It has high input impedance and low output impedance. That is a first stage of operational amplifier, that is a first block. So later on the output of first stage is connected to next block, that is called as an intermediate stage. So see here, in case of what is the need of intermediate state, so we know that when we talk about ideal characteristic of an operational amplifier, the gain is infinite. Okay, that means whenever the input is very very small, the output voltage is very large. So that is what ideal characteristics. So now overall gain is very high. That means, see, this first input stage amplifies signal, but that gain is not enough. So overall gain of the operational amplifier, which consists of all these stages, is very high. Only input stage cannot provide such a high gain. So this stage is not capable to provide very high gain, and for that the intermediate stage provides additional gain. That means the gain is increased by this intermediate stage. So that is a second block of operational amplifier. So now this is a third block, that is a buffer and level shifting. So remember that it brings down the DC level to ground potential when no input signal is applied to the input terminals. That means when no input signal is applied to the input terminals, but here the sources are there and we get some voltage at the input, which causes the amplification at the output, and which is basically a part of noise. So the buffers and level shifting, this block brings down the DC level to the ground potential. That is a purpose of this third block. And final stage is output stage. So it is a push-pull amplifier which provides large AC output voltage swing and high current sourcing and sinking along with the low output impedance. So we know that the characteristics of overall operational amplifier is that its output impedance is almost zero. So the purpose of this output stage is that it provides a very low output impedance, and that is why total current flows through the load connected at the output of the operational amplifier. So amount of current which is required is provided by this output stage. Okay, so it acts as a current sourcing as well as sinking. So this is the last stage, and including these four stages, the operational amplifier device is prepared. So let us see the actual integrated circuit which is used. Normally we use IC741. So here it is IC741. So we are talking about the pin diagram. So it is as shown in figure. It is 8 pin IC integrated circuit. So here it is a pin diagram, let us consider. So it has 8 terminals, and let us see what is the purpose of all those terminals. So see, here it is. Here it is a operational amplifier shown. So pin number 2 is connected for the inverting input. So inverting input is given to pin number 2. So here it is, first pin inverting that we saw. Second, we know that it has a positive, that is non-inverting terminal also. So here pin number 3 of this integrated circuit is for non-inverting input, and once both inputs are given, we know that there it is a one end that is called as output, that is pin number 6 gives the output for the operational amplifier. So apart from this, we know that for functioning of this operational amplifier we need a positive Vs and negative Vs. Okay, so that power supply, or we can say positive VCC and minus VEE, these two pins are there which gives power. So pin number 7 is for positive VCC and pin number 4 is for negative VEE. So these two pins are for especially for providing the power supply to this operational amplifier. Later on we know that in case of operational amplifier, we know that when no inputs are present, some output is present at the output, and that is called as a offset voltage. Okay, so to nullify the effect, there are two more pins which are making arrangement for offsetting. These are called as a offset pins. So here pin number 1 and pin number 5, these two pins are for offset null arrangement. So this way there are total 7 pins. See, these two pins for input inverting, pin number 2, non-inverting, pin number 3, output, pin number 6, for two power supplies, 7 number for positive VCC, 4 number for negative VEE, and 1 and 5 is for offset arrangement, and pin number 8 is of no connections. So this way the integrated circuit is formed. So this is a notch and left of the notch is pin number 1. So that you should remember while identifying the pins in the laboratory. Or sometimes there may be a dot near pin number 1. So these are the pin configurations of the practical operational amplifier. So now let us consider a very important and interesting concept of virtual ground in case of operational amplifier. So first you remember that we know that what is ground? Ground is actually a zero potential or 0 volt. But here we see the word that is a virtual ground. So practically in our circuit we always show that if some point is connected to ground, it is by this, which is called as a ground potential. But here the concept virtual ground, that means where the potential is 0, that concept we are going to see. So see here it is. In this case we know this is an operational amplifier. Okay, so when inputs are given to the operational amplifier and output is taken, so we know that its open loop gain AV, which is VO upon VI, that is infinite. That is first important thing we should remember. So here open loop gain AV is infinite. Now we know that AV is equal to VO upon VI, but in this case we know that there are two inputs. Here it is non-inverting, here it is inverting. So here the input is V1, here it is V2. And operational amplifier's first stage is what? It is a differential amplifier which gives the difference of the V1 and V2 at the output, so that you remember. So here potential V1 is connected to non-inverting terminal and V2 is connected to inverting terminal. So remember that these are the points where this V1 and V2 is present. So now when we connect, whenever it is open loop, so gain is infinite and obviously output voltage is also infinite. But remember, practically no circuit can give infinite voltage. So that means at this time the voltage at the output is at the saturation, and how much voltage is to be at the output, that depends on the Vsat, that means the VCC and VE provided to this. So never output voltage can be greater than that, you should remember. Practically we never get the infinite voltage. So here the gain, open loop gain is infinite, so maximum output and output voltage is at saturation. So in order to control the things, we are connecting the feedback resistance. So here we have connected the feedback resistance RF, which takes some part of the output voltage and gives it to the inverting input. So that is why the voltage difference between V1 and V2 changes, and automatically output voltage also changes. But the moment output voltage changes, again the value of feedback voltage also changes, and this way the amplifier try to stabilize the output voltage, and output voltage gets stabilized at certain point. So here this is connected, inverting terminal is also connected to input voltage V in through resistance R in. So that is the thing, and here it is V1. Now V1 is connected to the ground. So remember that when V1 is connected to the ground, means the potential at this point, V point of inverting non-inverting terminal, that is V is equal to 0 volt. That you should first remember. Now we are going to talk about how this V2 acts as a virtual ground. Practically if you see, the voltage is applied here through resistance, and that is why practically if we see that some potential is available here. But we are considering this point as a virtual ground, and why are we considering that? Let us consider. So see, input impedance, the characteristics of operational amplifier is that input impedance is infinite. That means between this terminal and this terminal, the input impedance, that is resistance, is infinite. So in short, you can understand, if this is one point and this is another point, and if resistance is infinite, that means obviously the input current, okay, that is equal to 0. Okay, so that remember that the current flowing between these two terminals is 0. So current never flows between this and this since input impedance is infinite. That is first thing which is to be remembered. So now that is why input bias current IB, which I have shown here, that IB is 0. Remember that here it is input impedance is infinite, and that is why current IB is 0. So when we talk about virtual ground concept, we know that VO, that is voltage gain, AV is equal to output voltage upon input voltage Vin. Okay, but in this case what is Vin? It is a difference of V1 and V2, so we can write that is AV is equal to VO upon V1 minus V2. It is a difference of these two inputs, that remember. But now we know that the gain of an amplifier AV, which is equal to VO upon V1 minus V2, is actually infinite. Okay, so how can this value tend to infinity, or why it should be infinite, that let us consider. So therefore, if we want this value AV to be infinite, so first important thing is that either the value of VO, that is actually VO should be infinite, but we know that no infinite voltage can be generated by any IC. Okay, so it goes to saturation and that value is controlled by the power supplies. Okay, so that is saturation. So that means VO can never be infinite. Now if VO cannot be infinite, so to become AV is infinite, the second condition is that if it is not possible, then V1 minus V2 must be 0. And if this is the case, then we can have an infinite gain. So therefore V1 is equal to V2. But we already know, remember that if we look back, that V2 is connected, this V1 is connected to ground. So when V1 is connected to ground, so potential of voltage of V1 is 0. So obviously when V1 is equal to V2, that is equal to 0. So this way we can say that whatever the potential here, the same potential is existing here, and that is why it is called as a virtual ground. And as whatever potential at this point and this point, when they are equal, remember that no current can flow through two equipotential points. That also you should remember. That is important thing, and that is why this point is called as a virtual ground. So this is a concept of virtual ground. So for further study, you remember that AV voltage gain is equal to V0 upon Vi. Okay, but we know that VO is equal to minus RF upon Ri into Vin. This is a relation, or we can say AV is equal to VO upon Vin, that is exactly equal to minus RF upon Ri. So remember that the ratio of gain of an operational amplifier in case of inverting, we can say gain is given by VO upon Vin, and that is exactly equal to minus RF upon Ri. So gain of the amplifier can be decided by the feedback resistance and input resistance. So now let us consider operational amplifier as non-inverting amplifier. So here in this figure you see this is operational amplifier. So first, before starting this, let us consider what is operational non-inverting amplifier. Remember that if this is an amplifier, if this is the input signal, okay, and if it is amplified but the phase is same. So look here, that this is this way the amplification is there, no phase change is there. It is called as a non-inverting amplifier. That is non-inverting amplifier. And if we talk about inverting amplifier, then if this is the input signal, then output will be amplified, but the phase change will be there. Okay, so that means this part is shifted by 180. So now let us consider non-inverting amplifier, in which if input is positive, output will be positive. So that kind of amplifier we are considering, and for that purpose we need to apply input voltage to non-inverting terminal, because of op-amp is operated in non-inverting mode. So Vin is connected to non-inverting terminal, and gain controlling resistors, that is Rf and R1, are connected to inverting terminal. So this is the case, that feedback resistance is connected between output to the inverting terminal, and R1 is connected between inverting terminal and ground. So this is a circuit diagram of an operational amplifier, and positive VCC and negative VE is provided for providing the supply. So see here, once the circuit is on, you can see that when input voltage is there, due to the difference between both input voltages, output voltage will appear, and when voltage appears at the output V out, which causes the flow of current through feedback resistance Rf, and that current is If. So current through feedback resistance is If. Now it is flowing from this output terminal to the input of an operational amplifier. Remember that this inverting and this non-inverting, these are called as the inputs of operational amplifier. Okay, this is output, and if we provide some voltage here or here, these are also called as a corresponding output. So here voltage current flows If through Rf. But second important thing, that we know the concept of input impedance. So input impedance is infinite of an operational amplifier. That means the resistance between inverting and non-inverting terminal is infinite, and so no current can flow between inverting and non-inverting terminal. So that is why whatever current If comes to inverting terminal, the same current flows through resistance R1, that is called as I1. Okay, so If is exactly equal to I1, provided that we are considering the operational amplifier ideal and there is a infinite input resistance at the input terminals. So here it is If and I1. Now remember that here we have a ground potential, here the potential at point V2, and here it is V out. So since input impedance is infinite, no current flows between inverting and non-inverting terminal. Therefore If is equal to I1. So whatever current If flows through feedback resistance, the same current flows through resistance R1. So therefore If is equal to I1. So that is current through feedback resistance is exactly equal to current through resistance R1, that we treat as a I1. So now let us apply Kirchhoff's current law. So these are two circuits. See, if you look at this circuit, that is, this is resistance R1. Okay, this is ground terminal, and another end is connected at potential V2. So this is connected to ground. So let us consider. So if this is potential V2, this is resistance R1, then we can easily find out the current I1 flowing through this. So I1 is equal to, according to Ohm's law, V is equal to IR. So I is equal to V upon R. So we can say that V2 upon R1 can gives us the current I1. So this way we can apply Kirchhoff's current law. But remember that whatever current I1 is flowing, that is exactly equal to current IF. So in this circuit, if we consider Kirchhoff's circuit in this case, so here the source of voltage is V out, that is, this is one source, then current IF flows through RF, and at another terminal there is another voltage source, that is V2. So in this network there are two voltage sources, V out, that you remember. So here Opamp applying KCL, if from figure IF is equal to VO minus V1 upon RF. So similarly, see here it is IF. So here there are two batteries, V out and V2. So difference of these two batteries actually causing current flow across RF. Therefore, IF is equal to V out minus V1 divided by RF. So from figure we know, we already saw, that is I1 is equal to V2 upon R1. So remember that these 2 points are equipotential points, that you remember, that we already saw virtual ground. So that means whatever, now we are applying input voltage here, V in. Okay, so whenever we apply V in here, so whatever voltage appears here, that voltage exactly becomes equal to V2 because of potential at both the terminals are same, the concept of virtual ground, and here in case of virtual shorts. So here it is, from figure I1 is equal to V1 upon R1. So see, if Opamp is ideal, that is V1 is equal to V in. So remember, here it is, this is potential at input terminal V1. Okay, but if operational amplifier is ideal, what does it mean? That means no input offset voltage etc. available. So in case of ideal operational amplifier, whatever V in will provide, that is exactly equal to V1. So we can replace V1 by V in. So therefore we can write current at the input terminal. Remember that this potential is now exactly equal to this. This V1 at this point is now V in. So current in this we can say that is V in upon R1 is equal to VO minus V in upon RF. So this is a comparison of I1 is equal to IF. So V1 is replaced by V in, and remember that this at this point, as both potentials are same, that is a V in. So therefore we can write, see here it is, from this V in into RF upon R1 is exactly equal to VO minus V in. So from this we get VO is equal to V in into 1 plus RF upon R1, and we know that voltage gain of an amplifier, that is a gain of the amplifier, is equal to VO upon V in. So VO upon V in is equal to 1 plus RF upon R1, and that is why in case of non-inverting amplifier, the gain of amplifier is 1 plus RF upon R1. The value of RF and R1 decides the gain of amplifier. This is non-inverting amplifier. If input is positive, output will be positive, and amplification can be controlled by the RF and R1 by adjusting the gain. So this is a concept of non-inverting amplifier using operational amplifier. Okay friends, so in next lecture we'll consider inverting amplifier. Okay, thank you very much. Thank you. Bye.